Hello everyone, welcome to my YouTube channel. Today I am going to teach the organometallic chemistry. So in this class I will give basic introduction to organometallic chemistry. I will tell how to count the effective atomic number, that is the EAN of an organometallic complex. So first we should know what is an organometallic compound. So an organometallic compound is broadly defined as one that involves one or more carbon atoms of an organic group or a molecule and a metal atom. So that means there was a bond between the metal and the carbon atom in the organometallic compound. So that will classify as a organometallic compound. So there should be minimum one bond between the metal and the carbon atom of this ligand moiety. So this is the example of a organometallic compound. There is this nickel CO whole 4 and another one is the FO iron CO whole 5. So here the metal is for the FeCO whole 5, the metal is iron and ligand is CO. So there is a bond between this carbon atom of this CO molecule and this iron molecule. So there is a metal carbon bond. So this is the example of a organometallic compound. So and now I will tell how many ligands present in this organometallic compound. So there are many types of ligand in this organometallic compound. So first I will classify the ligand on the basis of their charge. So on the basis of the charge, there are total two types of ligand. So on another one is the L-type ligand and another one is this X-type ligand. So L-type ligands means these ligands are derived from charge neutral precursors. That means this L-type ligand, they are the neutral species. The total charge is equal to 0. So that means they are electronically neutral. So the example of this L-type ligand is this CO molecule, this amines, and this water molecule. So here in this three molecule, there is no positive or negative charge. They are the neutral species. So they are they are named as a L-type ligand. And second one is this X-type ligand. So X-type ligand means ligands that are derived from anionic precursors. That means this ligand, the X-type ligands, it has overall negative charge on this molecule. So the example of this X-type ligand on is the hydroxide, this OH molecule, or halides. Halide means this Cl minus or I minus. So in these ligands have one negative charge on this hydroxide molecule, or one negative charge is iodide or chloride. So this is the X-type ligand. So in the X-type ligand has a overall negative charge on their molecule. So this is the two types of ligand, L and X, on the basis of the charge. So now this is a 1,3-butadiene molecule. So 1,3-butadiene molecule, it has 2 pi bond, carbon carbon double bond. So it will donate this Cc double pi electron density to the metal center. So and also this overall charge of this molecule is 0. So this is one is the one L and another L. So this is overall is a L2 type of ligand. So that means it has two donating side, and two donating side will donate total 4 electron to the metal center. So it is a L2 type of ligand. And another example is this allyl molecule. So structure of this allyl molecule is that so this is the structure. So this is the structure of the allylic molecule. So this is the structure of this allylic molecule. So it has one carbon-carbon double bond and another negative charge on this molecule. So it can donate this pi electron density to the metal center and also this negative charge to this metal center. So when it donates this pi electron, it will L-type manner, and when it donates this negative charge, it will in X-type manner. So here this is a condensation mode of this allyl molecule. It will donate via this total 3 carbon atom, and this overall electron density is localized over this 3 carbon atom. So it is a LX type of ligand. So that means it has total 3 electron for donation to the metal center. So next I will classify the ligand on their donating nature. So that means there are total mainly 3 types of ligand on their donating nature. So first one is the sigma donor ligand. So sigma donors ligands mean ligands that acts as a Lewis base and donating electron from a lone pair to the metal center. So that means the ligand that will donate its lone pair to the metal center. So example of this water molecule or this halide minus or OH minus, they will all are the sigma donor ligands. They will donate their lone pair that is in this HOMO to the metal center. And second one is this sigma donor and pi acceptor. So that this ligand that donate to the lone pair to the metal center, but also this ligand has the ability to accept the electron density from the metal d orbital to their empty pi orbital. So in the broader sense, this type of ligands can donate the electron to the metal center and also can accept the electron from the metal center into the vacant pi star orbital. So example of this sigma donor or pi acceptor ligand is this CO molecule or this Cn minus. So this is the electronic diagram of this sigma donor and the pi acceptor ligands. So here there is a lone pair on this carbon atom. It will donate this lone pair to the vacant d orbital of the metal, and this CO molecule has a vacant pi star orbital. So it will accept the electron from this field d orbital of the metal center. So that's why there is a electron donation and electron donation from the carbon atom and electron acceptance from the pi star metal center to the pi star orbital of this CO molecule. So this is the example of a sigma donor or pi acceptor ligands. And another one is the pi donor and pi acceptor. So pi donor and pi acceptor means the ligand that donate pi electron to the metal center and also the accept the electron from this metal d orbital to that empty pi star orbital. So the example of this pi donor pi acceptor molecule is the acetyl molecule or this ethylene molecule. So this is the electronic diagram of this pi donor pi acceptor ligand, the ethylene molecule. So ethylene molecule there as a carbon-carbon bond, so it will donate this pi electron to the metal center. So it donates the pi electron to the vacant d orbital of the metal, and also it will accept the electron from this vacant pi star orbital of this molecule. So basic difference between this sigma donor and this ligand is that sigma donor only donate the electron to the metal center, but for the case of sigma donor and pi acceptor and the pi donor and pi acceptor, it will also donate to the metal center, and it will also accept the electron from the metal center. So next I will classify the ligands on the number of donor side. So one is the first one is the monodentate ligand. So mono means it has only one donor site which is attached to the metal center. So that means the ligand that will donate via only one coordinated site. So that to the coordination site. So this that will called as a monodentate ligand. So monodentate ligand, the example is the CO molecule and water molecule or OH minus. These all are the monodentate ligand. It will has only one donor site which is directly attached to the metal center. And second one is the bidentate ligand. So bi means two. So that ligand that has two donor site that will donate the electron to the metal center. So bidentate ligands has total two donor site. So example of this bidentate ligand is that the ethylene diamine molecule. So ethylene diamine, there is total two nitrogen atom. So these two nitrogen atom can simultaneously donate electron to this metal center. So here it is a bidentate ligand system. And another one is the ethynyl molecule. It has total two carbon atom. So it will donate the metal center via these two carbon atoms. So it is also as a bidentate ligand system. So here one term is heptacity. Heptacity. So heptacity, this term will define the how many number of donor site present in this metal ligand system. So it will donate via this nita. So for this monodentate, it has only one donor site. So for this monodentate ligand, it will donate via this nita 1, and this bidentate ligand system has two donor site. So their heptacity is 2. So this will denote by this nita 2, and it also has this nita 2. And the polydentate and next one is the polydentate ligand system. So polydentate means it has more than two donor site which is attached to the metal center. So polydentate ligands has more than two donor site which is directly coordinated to the metal center. So one example is the benzene molecule. So is a benzene molecule is a pi donor ligand system. It has total 6 carbon atom. It has a total 6 carbon atom. So it will donate this pi electron to this metal center via this total 6 carbon atom. So here it is a heptadentate ligand system, and the heptacity of this benzene is 6. So it will denoted by this nita 6 fashion. And another one example is this allyl. This allyl moiety has total 3 donating site. This 3 carbon atom, it will donate to the metal center via this 3 metal. So here the heptacity is 3, and it will denoted by this nita 3. So next, another interesting ligand system which is called as the ambidentate ligands. So ambidentate means the ligands that have 2 or more donor atom, but only one atom is attached to the metal center during this complex formation. So that means the ligand that has more than two or more than two donor site who is capable of doing donation the electron to the metal center, but during the complex formation it will donate via only one donating side. So this is the amidanted ligand system. So example of this amidanted ligand system is NO2 minus and the CN minus. So for the NO2 minus, there is total two donating side. One is N and another one is O. So it can donate the electron to the metal center via N or via O. So when it donates the electron density via this N atom, it has nitrogen mode, and when it donates the electron to the O atom, it has nitrogen mode. So this is the example of the amidanted ligands. So next we will discuss the 18 electron rule. So 18 electron rule is the way to help us to decide whether a given metal complex is likely to be stable or not. So the 18 electron rule will suggest this metal complex has a stability or not. That means the organic molecule has follow the octet rule for their stability. So similarly, in this organometallic complex, they follow this 18 electron rule, which organometallic complex have the 18 electron rule. It will be more stable compared to the less electron in the valence electron or more electron. So the 18 electron valence organic metallic compound will be more stable compared to the other. So for this 18 electron rule, we have to count the total valence electron in this organometallic compound. So that is called the effective atomic number, this EAN. So EAN means number of valence electrons to the metal ion plus number of electron donated by the ligand. So that means for this effective atomic number counted, when we have to count the total valence electron in the metal center and also total number of electron donating by the ligands. So there are two procedure for this effective atomic number counting. One is the ionic model and another is the covalent method. So in ionic model, first we have to determine the overall charge of the complex, and then we have to identify the charge of the ligand and of the number of the electron they donate, and then we have to add up the total electron from the metal center with their oxidation state and electron from the ligands. So that means for ionic model we have to first determine the overall charge of the complex, then the oxidation state of the metal, and then the charges of the ligand and how many electrons they donated to the metal center, and then we have to add all those electron from the ligand and the valence electron of the metal with consideration of the oxidation state. So this is the basic rule of this ionic model. So there are total two types of ligand. One is L and one is X. So in this ionic model, both L and X type ligand will donate total 2 electron to the metal center. But L type ligand is a neutral ligand, so it will donate total 2 electron, but overall charge is 0. But for this X type ligand, it will donate 2 electron to the metal center, but it will give one negative charge to the total electron count. So next one is the covalent method. So for the covalent method, it is an electron neutral method. So for this case, we have to first identify the group number of the metal. That means in which group this metal is situated in the periodic table. And next, we have to identify the overall charge of the complex, whether the complex is electron neutral, or it is a positive charge or a negative charge. We have to identify this, and then we have to add up the group number of the metal plus electron from the ligand with the consideration of the overall charge of the complex. That means in this covalent method, we have to first identify the group number, then overall charge of the complex, then we have to add up this group number and the electron from the ligands with the consideration of overall charge. So in L and X, L type ligand will donate total 2 electron to the metal center in this covalent method, and X type ligand will donate 1 electron to the metal centers in this covalent method. So basic difference in this covalent method and ionic method is that in the ionic method, both L and X type ligand will donate 2 electrons to the metal center, but for the covalent method, the L type ligand will donate 2 electrons to the metal center, and the X type ligand will be donate 1 electron to the metal center. So I will give some example of the effective atomic number countant. So first one example is the MnBrCO whole 5. So manganese is a group 7 metal, so it has its valence electron configuration is 4s2 and 3d5. So in the valence it has total 7 electron, so in the manganese metal. So first I will count in the covalent method. So for the covalent method, we have to first identify the group number of the metal. So for manganese, the group number is 7, and next we will identify the overall charge of the complex. So here is a electronic neutral complex, so the overall charge of the complex is 0, and next we will add up all the electron from the metal center and this ligand system. So here total electron count is 80. So manganese is a group 7 metal, so it will donate total 7 electron, and this bromine is a X type ligand, so it will donate 1 electron in this covalent method, and carbonyl is a L type ligand, so it will donate total 2 electron. So there are total 5 carbonyl molecule, so here it will donate total 10 electron. So here total electron count is 18. So in this covalent method, MnBrCO whole 5 has total 18 electron. So in ionic method, we have to first determine the overall charge of the complex. So here overall charge of the complex is 0, and next we will identify the oxidation state of the complex. So here the MnBrCO whole 5 is in +1 oxidation state. So +1 oxidation state means its electron count is 4s1 3d5. So Mn+1 has total 6 electron in this valence electron. So, and Br is a X type ligand, so it will donate total 2 electron in this ionic method, and carbonyl is a L type ligand, so it will donate total 2 electron in this ionic method. So total electron count will be 6, that is from this Mn+1 oxidation state, and 2 from the bromine, and each here total 5 carbonyl, so it will donate total 10 electron. So overall electron count is 18. So in this covalent and ionic method, both electron count would same, but the procedure was different. So next example is CpMoCO whole 3 H2O, and the overall charge of the complex is +1. So molybdenum is group 6 its valence electron configuration is 4s1 d5. So it has total 5 electron in d orbital and 1 electron is the s orbital. So first we will count the EAN in covalent method. So for covalent method, we have to first identify the group number of the molybdenum. So the group number of molybdenum is 6, and CO is a L-type ligand, so it will donate total 2 electron to the metal center, and water also is a L-type ligand, so it will also donate 2 electron to the metal center, and Cp is a L2X type ligand, so that means it will donate total 5 electron in this electron count. So overall electron count in covalent method is that 6 from this molybdenum, it has group 6 metal, and total 6 from the carbonyl, total has 3 carbonyl, and it will donate total 2, so total 6 from carbonyl, and water is L type, so on one water molecule it will donate total 2, and Cp is L2X type ligand, so it will donate total 5 electron, and here the overall charge of the complex is +1, so we will subtract this one charge from, so here total electron count is 18. So now we will count the electron in this ionic method. So ionic method, here the oxidation state, we have to first identify the oxidation state of this metal. So here the molybdenum is this +2, so molybdenum in +2 oxidation state, that means it has total 4 electron in the d orbital, and Cp is a L2X type ligand. So in this ionic method, Cp will donate total 6 electron to the metal center, and carbonyl is a L type ligand, so it will donate total 2 electron to the metal center, and water is a L type, it also will donate total 2 electron to the metal center. So here effective atomic number is 18. So 4 valence electron from molybdenum 2, and each total 3 carbonyl, so it will donate, each will donate 2, so total 6 electron from the carbonyl, and water is the L type ligand, it will donate 2 electron, and Cp is the L2X type, so it will donate 6 electron in the ionic method, so overall electron count is 18. So next example is this nita-3 allyl hold to nickel. So nickel is group 10 metal, so it has electron count, valence electron configuration is 2d8, and this nita-3 allyl, it is a LX type ligand system, it will donate its negative charge or this pi bond to the metal center via these 3 carbon atom. So it is a LX type ligand. So first we will count the electron in the covalent method. So first for covalent method, we have to identify the group number of the nickel. So nickel is the group number is 10, and here this ligand is LX type. So LX mean it will donate total 3 electron. So here total 2. So effective atomic number for the nickel will contribute total 10 electron, and each allyl will contribute 3 and total 6 from this 2 allyl. So here the total atomic count is 16. So next, in the ionic method, so in ionic method we have to count, first identify the oxidation state of the metal center. So here nickel has two allyl ligand. So allyl ligand is a LX type ligand. So oxidation state of nickel is +2. So that means it has electronic configuration in the valence electron in d orbital. It has total d8. So that means it had d8 electron in the d orbital. And this allyl is LX type ligand. So in ionic method, it will donate total 4 electron to the metal center. So for the En calculation, so first nickel will contribute total 8 electron because it is in nickel +2 oxidation state. Next, this allyl will contribute total 4 electron. There are total 2 allylic ligand, so it will donate total 8 electron. So here this total 16 electron in this metal, in this organometallic compound. So next I will give the example of this nita5 C5H5 carbonyl Fe mu CO whole 2 FeCO nita5 C5H5. So this is the structure of this complex. So here each iron, here carbonyl is the bridging mode, and this is the terminal carbonyl, this is the bridging carbonyl, and one metal iron bond. So iron, so for the En calculation in the covalent method, we have to first identify the group number of the metal. So here iron is the group 8. So its valence electron configuration is 2d6. So it will donate total 8 electron in the En count. Next, this CO, it will donate total 2 electron to this metal center. This nita5 C5H5, that means it has L2 X type ligand, so it will donate total 5 electron. So it total 5 electron from this nita5 C5H5, and there are total 2 bridging CO. So in this terminal case, the CO will donate 2 electron. So here also in the bridging CO will donate 2 electron, but 1 electron to this iron and 1 electron to this iron. So that means it will give 1 electron to this and 1 electron to this. Similarly, this will give 1 electron to this and 1 electron to this. So here in covalent it will donate here total 2 bridging CO. It will donate total 2 electron to 1 iron center. So and another one, there is a iron metal bond. So for that 1 electron. So here total 18 electron for this complex in this covalent method. So next we will calculate the electron count for this ionic method. So for ionic method, we have to first identify the oxidation state of this iron. So here iron is +1 oxidation state. So +1 oxidation state, that means it has electronic configuration DS1 D6. So here total 7 valence electron, and CP C5H5, it is LX type. So in this ionic method, it will donate total 6 electron to the metal center. So En, for the En calculation, so here total 7 electron from the iron, it is a Fe plus 1 state, and here one terminal CO, it will donate total 2 electron, and here this Cp star eta 5, so it will donate. So Cp star has total Lx type, so it will donate total 6 electron to the metal center in this ionic method, and there are total 2 bridging carbonyl, so it will donate 1 to the 1 metal center, so total 2 from total 2 bridging CO, and there is a 1 metal bond, so it will donate 1. So here total 18 electron from this, for this each iron in this ionic model. So this is the example. We will understand, we will give the idea about how to count the electron effective atomic number of an organometallic compound. So this is the some example of the ligand, and so here this chloride Cl minus or pH minus, it will be X type ligand, it will donate 1 electron in the covalent method and 2 electron in the ionic method. This new CO and NH3 this is the electron neutral L type ligand, they will donate total 2 electron in both ionic and covalent method. And the C2H4, it is a pi-donor ligand, it is also L type ligand, so it will donate also 2 electron to in each in covalent and ionic method. So nita-3 allyl, it is Lx type ligand, it will donate 3 electron in the covalent method and 4 electron in this ionic method. So nita-4 butadiene, it has total 2 carbon-carbon bond, so it is a L2 type ligand, it will donate total 4 electron in both ionic and covalent method. So nita-5 Cp, it is a L2X type ligand, so it will donate 5 electron in the covalent method and 6 electron in the ionic method. And nita-6 benzene, it is a L3 type ligand, so it will donate 6 electron in both ionic and covalent method. Sure. Thank you.